All right, welcome to our control engineering final project. We chose to do the overhead crane problem. This project was created by Peter Taenzer, Joe Virga, Benjamin Thompson, and Patrick Keane. For the final project, our group chose to do the crane problem because we thought it would present an interesting challenge to our group, and few other groups were doing the crane. Also, we were interested in the fact that since the cranes would be indoors, there would be very little disturbance to them. Looking at the velocity in the objects carried by cranes, we thought this would be a very interesting problem to try to solve and overcome. Alright, to model our transfer function, we chose to implement a step function. You can see that created here along with the root locus and the block diagram for our function. Using different variables for our function, we set gravity equal to 9.81 meters per second and our length equal to 1 meter. We chose 1 meter because with an indoor crane, it won't be very long and we needed to pick a constant value, and 1's very easy to work with. Now looking at our poles, you can see we have 3 different poles, which is what we'd expect from our function. Now looking at just the pole specifically, you can't tell whether the system is stable or unstable. But when you look at the root locus, you can tell the system is unstable based on the fact that the poles move towards the right half plane. To fix this, we'll need to add zeros later on. To finish up our evaluation of the initial transfer function, we look at the step response. And when looking at the step response, you can see the graph exhibits a sinusoidal behavior. This is what we expect because as the crane moves, the weight it's carrying is going to oscillate back and forth. Comparing our step response to the given step response from the problem, you can see that they're both very similar. This is what we'd expect as we want our step response to look exactly like the example.
For the crane problem, the input is linear motion, which is caused by the worker who's moving the load, and this results in displacement of the load and angle of the cable. In order to maximize the input of the load, we wanted to make sure the system is stable so that when the worker is moving the load across, he can move it quickly and efficiently while not having the load swing back and hit them, causing the load to swing wildly. To make our system stable, we started off with the PI controller and then switched that over to a PD, and then we finally found out that the PD controller works the best, having both of our poles on the left half plane. As you can see, our transfer function in the top right corner going through the Routh-Horowitz and finding that our KD value, as long as it's greater than 0, will remain stable. And you can see our final transfer function right below that. Our system is stable when KD is greater than 0. Adding the 2 PD derivative controllers makes the response much faster and smoother in creating a more stable system. And as you can see, the Bode plot is on the left side. To the right of that, you can see the root locus and the step response. And then to the right of that, you've got the Nyquist diagram showing that the system is perfectly stable and very smooth.
Our team decided to use 2 PD controllers based off the root locus from the open loop transfer function. The open loop transfer function root locus shows that the 2 non-zero poles go off into the right half plane, meaning that it's unstable. By adding 1 PD controller, or 1 0, the poles begin to curve back towards the left half plane, but don't cross over into it. We then added another PD controller, which caused the poles to stay in the left half plane, meaning that the function will be stable. With no poles in the right half plane on the open loop transfer function, along with the Nyquist diagram never circling -1, we can also conclude that our transfer function will be stable. Some specifications that were important for our problem were rise time, steady state error, and overshoot. We wanted the rise time to remain under 1 second, the steady state error to remain close to 0, and the overshoot to remain under 3%. The overshoot is especially important as if the velocity oscillates, the mass will begin to swing out of control, causing potential harm to the operators. Based on the specifications given from our transfer function, we can see that the rise time is well under 1 second, there is no overshoot, and the steady state error goes to 0. Our team initially started by implementing a PI controller. The closed loop transfer function with the PI controller showed that the Routh-Horowitz had 2 holes in the right half plane. This is not okay because it makes the system unstable. An iteration we then made was to add the 2 PD controllers, adding zeros to the system. This made the system stable, as shown from the closed loop transfer function. We optimized our system by choosing K values of 0.2674 and 1.36. This gave us a rise time of 0.2 seconds, which is well under 1. This is important because the mass will get up to the desired velocity very quickly while maintaining zero overshoot so it does not oscillate out of control.
Looking at our Bode plot, we see that we have an infinite gain margin. This means that we cannot change our K values. Instead, we can look at the time delay, which is how long we can delay our system before it will become unstable. This value comes from the phase margin and omega crossover value, which is the omega that we read from the Bode plot where the magnitude crosses 0. Overall, this was a very challenging problem. It was nice to relate everything we have learned to a real-world problem. Our open loop system is unstable, but by adding the final controller we decided on, we were able to make a stable closed loop system that fits all of our design specifications. These were 0% overshoot, a 0 steady state error, and an infinite gain margin. All of this information provided shows that we were able to design a stable system. Have a great summer.